Ever pondered how mathematics mirrors real-world phenomena? Well, let's dive into the fascinating world of mathematical modeling, where this exact question finds its answer. Mathematical modeling is a method that uses mathematical language to describe a system. This system could be anything from population growth to the spread of diseases or even the dynamics of traffic. It's a way of creating a bridge between mathematics and the real world, and it's a bridge that's used in countless fields and disciplines. Let's take population growth, for instance. Mathematical models can be used to predict how a population will change over time, taking into account factors like birth and death rates, migration, and resources. These models are incredibly useful for policymakers, helping them make informed decisions about things like urban planning and resource allocation. Or consider the spread of diseases. With the help of mathematical models, we can predict how a disease might spread in a population, which can be critical in planning and implementing measures to control the spread of these diseases. For example, during the COVID-19 pandemic, mathematical models have been essential tools for understanding the disease's trajectory and for planning public health responses. Traffic dynamics are another area where mathematical modeling shines. Ever wondered how traffic lights are timed to optimize traffic flow? You guessed it, mathematical models. By understanding the traffic patterns and using mathematical models, engineers can design systems to minimize traffic congestion and improve overall transportation efficiency. The beauty of mathematical modeling lies in its ability to simplify and represent complex real-world scenarios. It's like having a universal translator that translates the language of the world into the language of mathematics and vice versa. So, the next time you're stuck in traffic or reading about the latest disease outbreak, remember, behind the scenes, mathematical models are hard at work, helping us understand these complex phenomena. And that's the magic of mathematics. It's not just numbers and equations, but a powerful tool that helps us make sense of the world. Mathematical modeling gives us a lens to view and understand the complexity of the world around us. Imagine having a tool to solve complex mathematical problems. Now let's delve into the world of numerical analysis. This branch of mathematics is all about the development of computational methods. These methods are not just theories on a blackboard, they are practical tools that provide solutions to some of the most intricate mathematical quandaries we face today. Take, for instance, partial differential equations. These equations are key in understanding various phenomena in the fields of engineering and physics. But they can be notoriously difficult to solve. Here's where numerical analysis steps in, providing computational methods that can handle these equations, even when they seem impenetrably complex. From predicting weather patterns to understanding the behavior of subatomic particles, these computational methodologies offer answers where traditional mathematical approaches may falter. They help us unlock new perspectives and possibilities in our quest for knowledge. Numerical analysis, thus, is the backbone of many scientific computations. What if you could find the best possible solution every time? Well, that's where the beauty of optimization comes into play. Optimization is like the compass of decision-making, always pointing towards the most efficient and effective route. Imagine you're managing a delivery service. You have multiple destinations and only a handful of drivers. The question is, how do you allocate these resources to ensure the quickest delivery times while minimizing fuel consumption? Well, this is where mathematical optimization techniques shine. They allow us to explore a myriad of possibilities and find the optimal solution. It's like having a supercomputer in your pocket, calculating every possible scenario and presenting you with the best one. From designing the quickest transportation routes to balancing resource allocation, optimization is the key that unlocks the door to efficiency. But it doesn't stop there. Optimization has applications in countless fields, from logistics and manufacturing to finance and computer science. Optimization, hence, is the secret sauce in efficient decision-making. Do you know how we predict weather or assess financial risks? Well, the answer lies in the fascinating world of statistics and probability. These two mathematical fields form the backbone of our ability to analyze data and make informed decisions. Imagine you're a meteorologist. To predict tomorrow's weather, you don't just stick your finger in the air and guess. You use statistical models built from years of collected data, analyzing patterns and probabilities to come up with the most likely weather scenario. Or consider a financial analyst assessing the risk of a particular investment. They don't just rely on their gut feeling. They use probability theories to calculate the likelihood of different outcomes, helping them make decisions that balance potential gains against possible risks. Even in clinical trials, statistics and probability are the unsung heroes. They help researchers determine the effectiveness of a new drug or treatment by comparing the outcomes of different groups. Statistics and probability, therefore, are the pillars of data-driven predictions. Ever wondered how your car's cruise control works? Well, welcome to the realm of control engineering. This fascinating field uses control theory to design automated control systems. It's the wizard behind the curtain of modern automation. Imagine the symphony of systems that work together when you set your car's cruise control. The car senses the speed, compares it to your set speed, and adjusts the throttle accordingly to maintain that speed. All of this happens thanks to control systems, a masterpiece of control engineering. And it's not just in your car. From the autopilot systems in aeronautics that keep our flight steady, to the robotics that assemble our gadgets, control engineering is everywhere. Electrical engineering too relies heavily on control systems to regulate power outputs and maintain system stability. So the next time you marvel at a piece of automated technology, remember the unsung hero, control engineering. It's the pulse of automation, ensuring our world ticks along smoothly. Control engineering thus is the pulse of automation. And there you have it. We've journeyed through the fascinating world of applied mathematics, discovering how it plays a pivotal role in representing and solving real-world phenomena. It's evident that the language of mathematics is not confined to the realm of abstract thought, but is deeply interwoven into the fabric of our everyday lives. Starting with mathematical modeling, we saw how equations and mathematical models are used to depict real-world scenarios. Whether it's predicting population growth, modeling the spread of a disease, or understanding traffic dynamics, mathematical models serve as our crystal ball, offering insights into future trends and behaviors. Next, we delved into numerical analysis, exploring the development of computational methods to tackle complex mathematical problems. The art of numerical analysis allows us to solve intricate equations that are commonplace in engineering or physics, enabling us to design bridges, predict weather patterns, and even send rockets to space. Then, we moved on to optimization. Here, mathematics morphs into a problem-solving powerhouse, finding optimal solutions in decision-making situations. Whether it's optimizing transportation routes to reduce travel time, planning production to minimize costs, or allocating resources to maximize efficiency, optimization is a cornerstone of strategic decision-making. We also dipped our toes into the vast ocean of statistics and probability. This field is instrumental in data analysis and decision-making. From weather forecasting to financial risk analysis and clinical trials, statistics and probability help us make sense of the world, turning raw data into actionable insights. Control engineering marked our next stop. Here we saw how control theory is employed to design automated control systems. From electrical engineering to aeronautics and robotics, control engineering ensures that systems function smoothly and efficiently, minimizing errors and maximizing productivity. But our mathematical journey doesn't end there. There are numerous other fields like computer science where mathematics is applied to programming, algorithms, cryptography, and machine learning. In fluid mechanics, partial differential equations describe the behavior of fluids, assisting in areas like aerodynamics, hydrodynamics, and chemical engineering. In the realm of mathematical finance, mathematical concepts are applied to asset valuation, risk management, and option pricing, helping us make sound financial decisions. Biometry uses statistics and probability to analyze biological data, contributing to epidemiological studies, population genetics, and clinical trial data analysis. And in computational geometry, geometry is applied in image processing, computer vision, and algorithm design to solve spatial problems. These are just a few glimpses into the myriad ways in which mathematics is applied. It's not just about numbers on a page or abstract equations. It's about using this powerful tool to solve real-world problems, make informed decisions, and understand the world around us in a more profound way. As you can see, mathematics is a powerful tool that finds application in solving real-world problems across a broad range of disciplines and sectors. Indeed, mathematics is the universal language of the universe.